bond energies and bond length. We learned how to calculate enthalpy changes, right? Okay, I explained how to calculate enthalpy changes back in chapter 6. There's another way that we can do that. It's not as accurate, but it can be used to estimate enthalpy changes for reactions. It's not necessarily easier, but it's another way to do it. And that is by using bond energies. The bond energy is the energy required to break 1 mole of that particular bond in the gas phase. How do you break a mole of bonds? Well, you break 1 bond each in a mole of molecules, okay? Bond energy is always positive. You always have to exert energy, put energy into the molecule to break the bond. The bonds do not spontaneously fall apart by themselves. Otherwise, the molecule would not stay together in the first place. If the bond is stronger, it's going to take more energy to break, right? So I talked about this in lecture yesterday. Maybe you guys know a name for this game. There used to be a game when I was in elementary school where you would hold on to somebody else's hand, grip their hand, and then somebody else would like try to karate chop and break your grip. Did you ever play that? They don't allow that in schools anymore because you can break your wrist, right? Well, that's Red Rover, and we'll get to Red Rover. Red Rover is my analogy for something else. But this is just chopping, breaking that. So the stronger your grip, the harder the person has to chop to break your grip, right? Children have done all kinds of stupid things. It's survival of the fittest, right? So the bond is stronger if it takes more energy to break. So here's an example. We're taking hydrogen chloride molecule in the gas state, and we're separating it into the 2 atoms. That requires 431 kilojoules of energy to break the bonds in 1 mole of HCl. If the bonds are stronger, the compound tends to be more stable and less reactive. So you can calculate, or really it's measuring, you can measure bond energies in different compounds, and they vary a little bit, even if it's a bond between the same 2 elements. So let's look at the carbon-hydrogen bond. In methane, that bond energy is 438 kilojoules. If we switch out the hydrogens for fluorine, the bond energy increases, 446. If we put bromine in there, it goes down, 402. We put chlorine in there, it's 401. And you can look at many different compounds that have carbon-hydrogen bonds, and the bond energy is going to be a little different in all of them. But we're estimating here, and so what we do is we average the carbon-hydrogen bond energy in a lot of different compounds, and then that's all given in tables. So we say the average carbon-hydrogen bond energy is 414 kilojoules, and we'll just use the average. Now, double and triple bonds have higher bond energies than single bonds, and this makes sense. So if you play that stupid hand-chopping game, and you're holding both of the hands of the other person, now you've got 2 grips, right? Is it going to take more energy to break through that? Yeah. And if you each grew a 3rd arm, right, and stuck another one in there, it would be even more. And bonds are like that too. A triple bond is stronger than a double bond. Here's a table from within your chapter. I think there's maybe another one in the back of the book that has some more bonds. But this is a table of bond energies, average bond energies. Let's look at carbon here. Carbon-carbon single bond, 347 kilojoules per mole. A double bond is stronger. It takes 611 kilojoules. Triple bond, 837 kilojoules. Now this is not it doubles with every bond or anything like that, but it increases. One I want to point out to you with this asterisk right here. A carbon-oxygen double bond, the average is 736, unless you're looking at carbon dioxide. It's 799 in carbon dioxide. And I think the reason they give the exception for that one is that it is quite significantly different than the average, and carbon dioxide is also a very common reactant and product, and so we run into it a lot. So just be aware of that. So how do we estimate enthalpy change using average bond energies? We look at the bonds that are breaking and the bonds that are being made. Breaking bonds is an endothermic process. You have to put energy into the molecule to break the bonds. Forming bonds is an exothermic process. Remember, law of conservation of energy? If I take something apart and that requires a certain amount of energy, doing the reverse should release the same amount of energy. So the numbers are the same, it's just the sign. Breaking a bond is endothermic, the energy is positive. Forming a bond is exothermic, the energy is negative. So what we do to estimate the heat of reaction is you add up all the bonds that are being broken, those are going to be positive numbers, and all the bonds that are being formed, those will be negative numbers. And the total is your estimated heat of reaction. Any questions?
So do we take those, so would the change be from the chart? And
Yes.
the bonds broken would be whatever's in the...
So if you're making a hydrogen-sulfur bond, it's going to be negative 368. If you're breaking it, it's positive 368.
Okay.
It's like if you're buying something from someone, you give them money. If they're selling it, if you're selling it to them, the opposite, then they give you money, right? There's no markup on this. Did you have a question? No? Okay. Let's do an example. Oh, let's look at a picture first. Forgot this was here. And this really is another application of Hess's law. So in this reaction, we're looking at methane reacting with chlorine. So in order for us to take these two structures and make them into these two structures, we have to pull one of these hydrogens off. We have to separate those two chlorines. And then we're going to put the chlorine on here, making a carbon-chlorine bond, and we're going to put the hydrogen on here. Think of making Legos, or think of this as being, funky Tinker Toys, right? So I've got this little structure with these balls that are stuck together. I have to pull this one off. That requires energy. And I have to pull these two apart. And then when these form, it releases energy. So it's positive to break. So we're breaking one carbon-hydrogen bond and one chlorine-chlorine bond, and then we're making a carbon-chlorine bond and a hydrogen-chlorine bond. If the total of that is negative, then this is a reaction that's going to release energy. Any questions? We often say that energy is stored in chemical bonds, right? That's the chemical energy. It's a form of potential energy. Breaking a chemical bond always requires energy. It's always endothermic. What happens is that an energy-rich compound undergoes reactions in which weak bonds are broken. It takes little energy to break those bonds, and strong bonds are formed, meaning there's a net release of a lot of energy. It's the forming of the chemical bonds that releases the energy. Here's the example. A potential future fuel is methanol. Write a balanced equation for the combustion of gaseous methanol and use bond energies to calculate the enthalpy of combustion of methanol in kilojoules per mole. So first we have to write an equation. So methanol combusting, CH3OH. When it combusts, what does it react with? Oxygen. O2, oxygen's diatomic. What are the products?
CO2.
Water and CO2. And that's something we learned already. If you have a compound containing carbon and hydrogen and possibly oxygen that's burning, the products are always the same, carbon dioxide and water. So then we have to balance it. 1 carbon and 1 carbon. I'm going to leave the oxygens for last. Here I've got 4 hydrogens, right? Over here I have 2, so I'll put a 2 there. We have 4 hydrogens. And now I'm going to look at my oxygens. I've got 2 oxygens here and 2 oxygens there, so a total of 4 oxygens on that side, and I've got 3 on that side. How can I get 4?
You have to change, let's make it 6 on one side. And
Yeah, this is the odd-even problem. There's different ways to think about approaching this, but I can't have this odd number and end up with evens over here. So one approach is just to double things, right? So if I put a 2 here, well, that's going to mess up some other things, but we can deal with that. Then I need a 2 in front of the CO2 for the carbons to be balanced. And I need a 4 in front of the water for the hydrogens to be balanced. Because I've got a total of 8 hydrogens, and now I've got 8 hydrogens. Now let's look at the oxygens again. Here I've got 2 times 2 is 4, and 4, we've got 8 over here, and now we've got 2 plus 2. So if I make this a 3, I'll get 8. So,
Aren't there 7 hydrogens on the line?
no, there's 8. There's 3 and 1. Everybody okay with that? Okay, so we wrote the balanced chemical equation. Use bond energies to calculate the enthalpy of combustion. There's 2 approaches to this. You can look at actual bonds that are being broken and formed, or you can say, I don't want to worry about it. I'd rather just pretend that I'm breaking all the bonds and forming all the bonds. And it's kind of a matter of individual preference. Some people, when they're building with Legos, and there's existing structures, they'll just pick pieces off and kind of recombine them. Other people want to take it down to loose Lego blocks, right, and just build from scratch. That's the difference between these 2 methods. So what do you guys want to do? Do all of them, or just do the ones that actually change? Let's do the ones that actually change. If you want to see breaking all of them and forming all of them, I did that yesterday, and so that's in the Monday, Wednesday playlist. So you could look at it that way. We kind of have to look at Lewis structures for these, because it's hard to look at this and just see what bonds are being broken, right? So we know how to draw Lewis structures. So I'm going to just do these quickly, because drawing Lewis structures is not the point of this problem. Then we've got oxygen. Actually, we've got 3 oxygens, don't we?
So when you're drawing those, you're not drawing it with the balanced equation stuff?
Well, yeah, I am.
Why aren't you drawing 2 carbon?
2 methanols, because I didn't start out that way. Oops. I'm being out of order. And then we're going to have 2 CO2s. And 4 water molecules. We're being so quiet that we can listen to the conversations in the next room. Okay. I'm going to draw a line here so that we don't get confused about what are reactants and what are products. So maybe let's do this. I'm going to make red all the bonds that are being broken. I really think this method is more difficult, but we're going to do it anyway.
Are you going to show us your method after?
Well, you can go to the YouTube video and see it. Breaking all the bonds and forming all the bonds. So, is any of this going to stay intact?
Maybe the C and the.
Well, but this is a single bond and that's a double bond. But here's hydrogen, oxygen, right? So this hydrogen, oxygen stayed together. But I broke this one and this one and that one and this one. Breaking that one.
Now, why are you saying that?
Well, because I do not have any oxygen-oxygen double bonds in my products.
Okay.
I don't have any carbon-hydrogen bonds or carbon-oxygen single bonds in the products. I do have oxygen-hydrogen single bonds. You know, I really don't think this is a good idea. I really don't. No, we're not. We're going to do it the other way. Because then we have to go figure out that, oh, we only had 2 of these that didn't reform and we've got all these others, and you know what? It's more confusing. So I'm not a fan of more confusing. If we have choices, I prefer less confusing. Isn't less confusing nicer? Yeah, it is. Oh, I shouldn't have erased all my H2Os. I still need an H2O over here. Okay. So we tried doing that. It wasn't very nice. And so we're just going to break all the bonds here and here and form all the bonds here. Okay, so let's tally up the types of bonds that we have. So we have I'm going to go to a different color here. We have hydrogen-oxygen bonds, single bonds, right? We have 2 of these molecules. Each of them has 1 hydrogen-oxygen bond. Okay, so we have 2 hydrogen-oxygen single bonds that are going to be broken. Also in this molecule, we have an oxygen-carbon single bond. In this molecule, there is 1 oxygen-carbon single bond. We have 2 molecules, so we're breaking 2 of those bonds. You with me? We also have carbon-hydrogen single bonds. How many of those in this molecule? 3. We have 2 molecules, so how many bonds? 6. So did we miss anything in here? I think we got all the bonds. And then we have this oxygen-oxygen double bond. How many of those are getting broken? 3. So now what we need to do is we need to go to the table and find the energies required to break these. Okay, so, can't see this, it's too small. We had, I'm writing this on the chalkboard because I hate flipping back and forth. Carbon-hydrogen single bond was 414. Hydrogen-oxygen single bond is 464. There was an oxygen-oxygen double bond, it's 498. And And we have carbon-oxygen. What about bold?
Why is the O double bond with O bolded in bold?
I don't know. You'd have
Just diatomic maybe.
You'd have to ask the publisher.
It's not.
I think it's just a figment of pixels or something. You know how sometimes fonts look weird? I don't think it's actually bolded.
All these values are due to the same.
Yes, you do not memorize these. I always have students asking me the craziest things. Do we need to memorize all the bond energies?
You never know what we'll expect.
No, you don't. Okay. So, the hydrogen-oxygen was 464, and we have two of them. So we've got 2 times 464. And the carbon-oxygen single bond was 360. There's 2 times 360. Carbon-hydrogen, we have 6 of those, times 414. And oxygen-oxygen double bond is 498. And we had 3 of those.
Yeah, that will, like for those on the very far left, and you have the like 2H to O, how did you read that from your Lewis structure?
So I looked at the molecule. This is one molecule, and there is one hydrogen-oxygen single bond in this molecule.
Okay.
I have 2 molecules, so I multiply that by 2.
Okay.
Because I want to get all the bonds with the stoichiometry up here.
Okay, so you want to write the actual components without the balanced part, and then you take that into account after when you do that.
It's kind of up to you whether you think of the, if you wanted to, you could just draw 2 of these and then count. I'm looking at 1 and then multiplying by the coefficient, because that's what makes sense to me. So let's take all these numbers here and add them up. 2 times 464, 1760.
No, I'm just guessing.
2 times 360, 6 times 414, 3 times 498. $56.26. That's the amount of energy to. You got a question?
Yeah, does formal charge ever come into play? Because if that's not the ideal structure might have a double bond. Which might
You have to draw the correct Lewis structure.
So you need the one with formal charge equaling 0.
Formal charges equaling 0 or as low as possible.
And then for the formal charges, do they have to all be 0, or just as many as possible?
For formal charges, you get them as low as possible. It is not always possible to have them be 0. In a polyatomic ion that has a charge, there has to be formal charge somewhere, because there's actual charge. Yes?
So the numbers, the bottom, the energy needed to break all the bonds?
Yeah. So it would take 5,626 kilojoules to take 2 moles of methanol and 3 moles of oxygen and separate them into atoms.
Like all of them?
All of them into individual atoms to break all of these bonds. So if we think of these as Legos, we're taking all of them apart so we just have individual Lego blocks. Nothing is connected to each other. Is that what actually happens in the chemical reaction? Absolutely not. But Hess's law says that doesn't matter. We can take any path we want as long as we start at the same place and end up at the same place. That's what state functions allow us to do. So this is the amount of energy needed to break all of those bonds. Now let's look at the amount of energy that will be released when we form all these bonds. Okay, so I'm going to make these green. Oh, that's not the right green. So what do we have going on over here? Well, we have carbon-oxygen double bonds. In one molecule, we have 2 of them, and we have 2 molecules. How many carbon-oxygen double bonds are we forming? 4. To make this molecule, we have to make 2 carbon-oxygen double bonds. And we want to make 2 molecules, so we need 4 of those bonds forming. and then there's water. In each water molecule, there are 2 oxygen-hydrogen single bonds. See that? 1, 2. We have 4 of those molecules. So we're going to have 8 of those. So I've got the hydrogen-oxygen. That's 464. And I happen to remember the bond energy for double bond in carbon dioxide is 799. And 4 of those. Oh, but these are negative, aren't they? Because energy is being released. So I have 4 times negative 799.
This is combustion reaction.
This is a combustion reaction, yes. Plus 8 times negative 464. And this is a total of minus 6908.
So then would you do the first one minus?
No, you don't do the first one minus that, because this is the energy required, and this is the energy released. You just add them together.
And that's what that equation was, the heat of the reaction.
Yep. So 626 kilojoules plus negative 6908 kilojoules. Minus 1282 kilojoules. This is the amount of energy released when this reaction as written happens, when you burn 2 moles of methanol. What I think is sneaky about this question is it wants the enthalpy of combustion for methyl in kilojoules per mole. You get this many kilojoules for 2 moles. So minus 1282 kilojoules for 2 moles of methanol. Because that's what's in the equation. If you burn 1 mole of methanol, you get half as much energy. So we need to take the 1282 and divide by 2. So that's negative 641 kilojoules per mole. Any questions?
And that's because it's releasing, right?
Yeah, it's negative because it's releasing energy. Because we take the point of view of the reaction. The reaction is losing energy, that's negative. Any other questions? Bond lengths. The bond length, we always talk about average. The average bond length is the average length of a bond between 2 particular atoms, again, in a large number of compounds. Double bonds are shorter than single, triple are shorter than double. And here's a comparison. The triple bond is 120 picometers, the double is 134 picometers, the carbon single bond is 154 picometers. In general, the longer bond is weaker and the shorter bond is stronger, but there are exceptions, of course. Well, of course. There's a table of bond lengths if you're interested. Actually, it's there even if you're not interested.